Okay, today we're going to be talking about confidence intervals. And throughout this lecture, what we'll do is we will conceptualize the understanding of confidence intervals, we'll calculate them, and we'll apply them. The calculation and application will go together in this instance. So to recap, we discussed t-tests, and if you recall, t-tests, what they do is they compare the mean of various samples and identify whether those means are significantly different. And we're identifying whether those differences are due to sampling error or because of some external force, some independent variable. So, for example, putting somebody on a weight loss program and comparing those people's weight loss averages to people who weren't on the program, right? So putting the weight loss program would be the independent variable in this case. We also discussed effect sizes. Now, effect sizes simply indicate the magnitude of an independent variable's impact. So the extent, so the level of impact that the weight loss program had on people who were part of the program. And today we're going to be talking about confidence intervals. So confidence intervals, essentially what they do is they estimate population parameters based on sample parameters, right? So if we don't have the mean for the population, we can use the sample that we currently have as an indicator of the population parameter. And you'll see what I'm talking about. So if we don't have data for the population, we can generate those data within some level of confidence for the population based on the sample that we have. And so again, these are based on sample parameters, and what it does is the intervals part of this is significant. So it gives a range with some confidence of the population. So it gives intervals or a range for the population parameters, and and the confidence intervals will state that the population mean will be between x and y, for example. And the logic here is that, and we use the confidence interval because samples don't reflect the population 100% of the time, or actually most likely ever. So what we want to do is we want to give some range that we believe that the population parameters will fit under. And so that's why we give the interval or the range. And so what this does is it accounts for the differences between the sample and the population. So it's not enough just to say that our sample mean is 3.5, therefore the population mean is 3.5, because we have to count for the sampling error that's taking place. And so essentially what we're doing here is we're taking a population with an unknown mean, and we're taking a sample from that population, and we're generating data based on that sample, and then we're going back and estimating the population parameters based on our sample data and giving a plausible range for that population. So to conceptualize, just to run back, confidence intervals are estimates of population values or population parameters based on the sample mean plus or minus sampling error. Or I should say plus and minus sampling error. So let's apply this concept and calculate it. So say you're interested in figuring out the average height of all Pac-12 basketball players. So this is your population of interest, right? Pac-12 basketball players. However, you only have access to players at University of Washington. There are 15 players with a mean of 78.2 inches tall, standard deviation of 3.67 inches tall. Let's just say this is pre-internet. That's why you only have access to UW players. So how can you estimate the population parameters, or the average height of Pac-12 players, without having the data, or only having the data from the UW's players? We can use confidence intervals for this, and that's exactly what we'll do. So the needed parameters, the parameters you need for this include the n, the mean, the standard deviation, and the standard error of the mean. And the standard error of the mean is calculated using the n and the standard deviation. And so the upper boundary equation is the mean plus the t value of the critical interval times the standard error of the mean. And alternatively, the lower boundary is the same equation, except we're subtracting the t of the confidence interval times the standard error of the mean. So it's pretty much the same equation, except we have the plus here and the minus here. And so let's talk about this guy here, this t of the confidence interval. Where do we get that? So the t of the confidence interval is the two-tailed critical value t-test, and we base this on degrees of freedom, right? And so this is the Appendix B in your book. And if we use the column, if we're looking at the book and we use the column that has an alpha level of 0.05, that indicates that we're giving 95% confidence that that population parameter will fall within that range. If we use the alpha level of 0.01, we're saying that we have 99% confidence that the population parameter will be in range. So what we need to do is we need to find our critical t based on our degrees of freedom, and then find that specific number. And so we'll go on to calculate this, and you'll see what I'm saying. So let's calculate basketball player height for the Pac-12. And so what we have here is we have an N of 15, so there are 15 basketball players on the University of Washington team. They have an average height of 78.2 inches and a standard deviation of 3.67 inches. So now we need to find the standard error of the mean. And if you remember back to t-testing, the standard error of the mean is simply the standard deviation divided by the square root of the sample size. And so overall what we get here is an SEM, standard error of the mean, of 0.95. And then we need to get our degrees of freedom. So if you remember back again to the T lectures and stuff about t-tests in the book, degrees of freedom is n minus 1. So in this case, we have 15 minus 1, which equals 14. And we're going to use that 14 to identify our critical t. So what we want to do is we want to identify the 95% critical t at 14 degrees of freedom. So if we go into our book, go into Appendix B, and we go down the column that has an alpha level of 0.05, because we have the 95%, right? So alpha level of 0.05 means 95% confidence. Then we'll have a t value of 2.1448, and we'll use that number to plug into the equation. So in this, the upper boundary here is the mean plus the t value. So we'll go ahead and calculate this here. So we plug in the mean of 78.2, which we find here, and then we add our critical t value of 2.1448 and times that by our standard error of the mean. And I'll give you a second to calculate that. And what we find for our upper boundary is 80.3 inches. Now, if your calculation is slightly different, I'm using Excel to calculate all of my data here, so it's going to be mine's going to be slightly more accurate if you're rounding, for example. Now, the lower boundary, we have the same equation, right? So we have m minus the critical t times the standard error of the mean for the sample. And so again, we can just plug these numbers in. And here we get a lower boundary of 76.10 inches. So again, like I said, I'm using Excel, so my decimals are going to be spread out a little further. So my calculations are going to be slightly more accurate here. So what this is telling me is that I can say with 95% confidence that the average height for Pac-12 basketball players is between 76.17 inches at the lower boundary and 80.23 inches at the upper boundary, or roughly 6'4" to 6'8". And I apologize, I just realized the numbers here don't match the slide before, so let me go back and reiterate this. I recalculated and changed the numbers here. So as I mentioned, there's gonna be some potential differences in rounding, but This is the most accurate number here, 80.23 inches, 76.17 inches. So basically what this is saying is that I can say with 95% confidence that the average height for Pac-12 basketball players is between 76.17 at the lower boundary and 80.23 at the upper boundary. Or in essence, the average height for basketball players in the Pac-12 is going to range from about 6'4" to 6'8" inches. Now again, note that this is not everybody is going. It's not saying that everybody is going to fit within 6'4" to 6'8", because there are players who are shorter and there are players who are taller. What this is saying is that the average of all those players is going to fit within this range, and I'll give that 95% that that's the case. And given that this is real data, I will say that that's the case. That's the purpose of using confidence intervals, right? So I could tell ESPN, for example, that the average height of all Pac-12 players is going to range between 6'4" and 6'8". So let's continue this. There's sort of an additional application here. So say you're interested in figuring out the mean difference in height of Pac-12 football players and Pac-12 basketball players. However, you only have players at the University of Washington. So we get the parameters for the basketball players at UW, and again it's the same as before. And then additionally we get the football players parameters. And again, these are real data. This is data I took off of the internet. So we want to know what the average difference is in the mean for the population of football players versus basketball players, using these two as samples. And again, how we do this is we need to take the same data. So we need to find the standard error of the mean and degrees of freedom using the same calculation for the independent samples t-test. So we use the same equation for the independent samples t-test to calculate the standard error of the mean. And because this is a fairly long equation, I'm just going to give the final result here. Feel free to go back and get the equation from your t-test, and it's also in the chapter on confidence intervals. So get that and calculate this out if you're interested. But the final result here is 1.79. Degrees of freedom is the N of the basketball team minus 1 plus the N of the football team minus 1, which gives us 1.15. And this is where we're going to find our critical T, right? We go to the degrees of freedom column in our appendix B and get the 95% critical T. In this case equals 1.9808. And the upper boundary here, our calculation is slightly different, but it's fairly similar, or it's pretty much the same, it's just slightly different. We're taking the difference between the mean of group 1 and the mean of group 2, so the mean of group 1 minus the mean of group 2, plus our t value, plus our standard error of the mean for the independent samples. And we plug in our numbers, and I'll give you a second to calculate this. And what you should have got is something around 8.11 inches. Now again, there's going to be some slight rounding error, so just be aware of that. But you should get something very close to, if not exactly, 8.11 inches. Our lower boundary, again, is the same equation. Excuse me, there's a typo here. This should say M1 minus M2, and I'll just change that quickly. Okay, so that's changed. So the equation is here, M1 minus M2, so mean of group 1 minus mean of group 2, minus the T of the confidence interval and the standard error of the mean, and this should be I, not S. Don't use previous slides. I've told myself that before. So anyway, plug the numbers in, and we get our final score of 1.01 inches. So what is this telling us? This is the question of interest, right? This is saying, I can say with 95% confidence that the average difference in height between Pac-12 basketball players and football players is between 1.01 inches at the lower level and 8.11 inches at the upper level. So basketball players are quite a bit taller than football players, and we have our range of confidence here, right? So we're 95% confident that the average difference is going to be somewhere between about 1 inch and 8 inches. So what we've done is we've conceptualized population estimates and population values with confidence intervals. We've discussed calculating confidence intervals for a single sample with the upper boundary and lower boundary, and independent samples and the difference between the samples for the upper boundary and lower boundary. We've also applied that. So what I want you to do is, I've given you a practice problem here. So say you want to know the average GPA of UW stat students, so that's your population, but you only have access to your class. This is your sample. An N of 32, mean of 3.23, and a standard deviation of 0.09. This is not real data. You want to know the difference in average stats GPA for UW Seattle students, but you only have access to one class. So what I'd like you to do is calculate the 95% confidence intervals for each population, calculate the 95% confidence intervals for the difference between the populations, and then a bonus, calculate each of the above using the 99% intervals, right? So you're going to find the 99% interval instead of the 95. And the next slide gives you the answers to the problem. So what you can do is you can pause the talk now and use this for your data and start plugging away. And then the next slide, this here, will give you the answers. So UW population, the upper boundary is going to be 3.26. Lower boundary is going to be 3.19. And note that your sample mean should fall within this. If it doesn't, then the calculation is going to be incorrect. Your mean should fall right within this boundary, right, for the sample, because we're using that to estimate the population. For UW Seattle students, the upper boundary is 2.51, lower boundary 2.17. And we have a difference here, so the average difference in UW stat students and UW Seattle stat students is 0.95 and 0.83 for the upper and lower boundaries respectively. So use these and use these as practice problems and go ahead and calculate the confidence intervals.